Today's speaker is Wei Wang from Xi'an University, China, and he's going to, the talk is entitled "Which graphs are determined by their total number of walks." Wei, it's all yours.
Okay. It is actually my great pleasure to give a talk at a Waterloo Algebraic Graph Theory seminar. I'm very, first I'd like to thank the organizer, especially Professor Gossel, for the invitation. So this is a joint work with my PhD student, Weifang Lv, and Finjin Liu is a professor at the Chang'an University. And there is another author is Wei Wang, another Wei Wang from Anhui Polytechnical University. So first, I'd like to give some introduction to give some motivations why we study this problem. Okay, I think the biggest motivation for us to study this problem is from the graph isomorphism problem. Given two graphs G and H, the problem just asks you to determine whether they are isomorphic or not. So despite many efforts, the GI, whether the problem is P or NP complete, is still undecided. So natural question is, can we use various graph invariants, such as the characteristic polynomial or the chromatic polynomial, and so on, as the tools to distinguish graphs? So in this talk, we try to distinguish graphs by their total number of walks. So walks and closed walks are very basic objects of study in graph theory. And they capture a lot of important structural information of graphs. For example, the works of length 0, just the number, just the number of vertex, and the number of the works of length there have some structural meaning, I think. So by a walk of length k in a graph, we mean a sequence of vertices and the edges. They appear alternatively, such that for every ei is 2 endpoints in the v subscript I-1, v subscript I. So I think this is a very basic object of study. And the work is closed if the starting point coincides with the ending point. So we shall denote by n subscript k capital G, and this guy to denote the number of walks and the closed walks of length k in a graph. So we shall use two notations. So the problem is, can we distinguish graphs by the sequence of this nkg and nkcg? Let's look at the problem from another view. So a homomorphism of a graph H to a graph G is just a mapping from the vertex of H to the vertex set of G, such that FU, FV is the edge of G, but whenever UV is the edge of H. So we use this notation, HOM, HJ, for the set of homomorphism from H to J. And for non-negative integer k, we denote by P subscript k and C subscript k, the paths and the circles of length k respectively. So a k walk, you can regard a k walk as a homomorphism in this set. Also, a k closed walk is a homomorphism from CK to G. So another definition is a left script H profile of G. It's just a vector. Here, H belongs to the script. It's a family of graphs, actually. So this denotes the cardinality of the homomorphism from H to J. So this is a vector. So a graph is determined by the left H profile if H is isomorphic to H prime, whenever H prime has the same left H profile as G. So actually this definition, I think, is appear in this paper, Lv's in 1967. So he studied this problem in that paper. So let's denote script H by this one, PK, all the paths of length K. We allow K to be 0. K is greater than or equal to 0. Then the graph G is determined by its left H profile, if only if G is determined by its total number of walks. If we denote this one, use this notation, H is another family of graphs. It consists of all the cycles, including the isolated versions. Then the graph G is determined by its left H profile, if only if G is determined by its total number of closed works. So from this we can see our previous problem actually you can consider in this general setting, I think. So in this talk, we're mainly concerned with this problem, which graphs are determined by the total number of works. This is by this the sequence, the infinite sequence, NKJ. This is NKJ denote the number of works of length K. So the same question for closed works is precisely the problem of the spectral characterizations of graphs. And we show for most graphs, the above problem is equivalent to the problem of generalized spectral characterizations of graphs, which the topic has been studied extensively in recent years. And by this observation, then we can give some simple criterions for a graph G to be determined by total number of works. Then later I will show you some examples. So actually, I will show later, our problem is closely related to the spectral characterizations of graphs. So which asks what kinds of graphs are determined by their spectrum. So in 2003 paper by Van Dam and Hemes, this is a survey paper, they raised this question. Actually, this question was raised earlier in 1956 by two chemists. And it's also related to some other problems, such as the coherent shape of a drum. So as it turned out, our problem is closely related to the spectral uniqueness of graphs. So before I go into the details, I give some notations and terminologies. I use G, VE to denote a graph with vertex set V and S set E. So I think everybody knows this generalization matrix and the characteristic polynomial. And also we can have the adjacency matrix. Adjacency matrix just the adjacency spectrum of the adjacency matrix. And the generalized spectrum of the graph G is defined to be the spectrum of G together with that of its complement. So it's the ordered pair. We're using this notation to denote the generalized spectrum. And a paragraph G and H are co-spectral if they have the same spectrum. A paragraph G and H are generalized spectral if they are co-spectral, and so are their complements. And the graph G is determined by its spectrum, we call DS for short. If any graph H that is co-spectral with G is isomorphic to G. So we call a graph is determined by its generalized spectrum, we call DGS. If any graph H that is generalized co-spectral with G is isomorphic to G. So this is a basic definitions. And the number of closed works And the spectrum, I think, is there is a close relationship. If two graph GH are co-spectral, then they have the same number of closed works of any length, actually. So this can be seen from the, I think, from the simple formula. Suppose A is the agency matrix of the graph, then A to the power, to the case power, suppose the edges element is this guy, then we have this formula. From this formula, it's easy to obtain that GH are co-spectral if only if they have the same number of closed works. And also we need some definition. Graph, eigenvalue lambda of a graph is said to be simple if its multiplicity is 1, and main if the corresponding eigenspace S lambda contains the eigenvector which is not orthogonal to the O1 vector. We let mu1, mu2 up to mu r be the total main eigenvalues of graph G. Then the main polynomial of the graph G is divided in this way, work matrix. The work matrix of graph G is defined as WG. The first column is O1 vector. The second is A multiply E. We divide it in this way, where E is the O1 vector. So the edges entrant of W is the number of works in the graph G of length G minus 1 that started at vertex I. So it turns out that the arithmetic property of W is closely related to whether the graph G is determined by its generalized spectrum. And recently, Liu and Simons, they showed that a graph G is determined by its work matrix WG whenever the rank of WG is greater than or equal to n minus 2. But our problem, which graph is determined by their total number of works, is some sense weaker, I think. In here, they want use WG to recover the graph, but we just know the information of the sequence of the work numbers. So we want to use this information to recover the graph. So here is another definition, a Hankel matrix, actually defined this way. It's WG transpose multiply WG. So it's a n by n matrix. It looks like this. So it's a Hankel matrix consisting of the numbers of works of length up to n times 2 times n minus 2 of G. So if we know the information of the number of works of G of length up to 2n minus 2, then we have this matrix and the Hankel matrix. This matrix, I think, plays an important role in our later discussions. So our main result is like this. We show, suppose Nj, the rank of Nj is greater than or equal to n minus 1, then J and H are generalized co-spectral, if only if Nkj equal to Nkh for k up to 2n minus 2, and if only if Nkj equals Nkh for all k greater than or equal to 0. So based on this theorem, we are able to give some criteria. We then reduce our original problem to the problem of generalized spectral characterizations of graphs. Then later we can give some criterion whether the graph G is determined by its total number of works in terms of the matrix, the Hankel matrix Ng. So actually, next we will show for the sequence of work numbers. for this one, actually they contain the same information, So actually we do not need all the informations of the work numbers. We just need the work numbers of length up to 2n minus 2. So here is the definition for the work generating function. It's like this. So we have a lemma. Suppose let G and H be two graphs with work matrix WG and WH and the work generating functions, this one and this one. Then they have the same generating function if only if NJ equals NH. That means their Hankel matrix coincides. So the proof of this lemma is based on another result of a termination in 2001. So we need this lemma. It says the number of main eigenvalues of graph G is R if only if there exists rational numbers A1 up to AR such that this equation holds. So basically the recurrence relation. And R is the smallest positive integer with this property. And if mu1, mu2, mu_r are the main eigenvalues of G, then the main eigenvalue, the main characteristic polynomial can be expressed in this way. So from this relation, we can give a very short proof. So I think I shall not go into the details. I think the proof is not too difficult. So from this, we can see, suppose the rank of NJ is greater than equal to 1, and greater than equal to n minus 1. Then NKJ equal to NKH for two graphs JH, if only they have the same characteristic polynomial, and also they have the same characteristic polynomial for their complements. So that means GH are generalized co-spectral. So from here we see for almost a graph G, we already know for almost a graph G is determinant of the WG is not equal to 0. So by this paper. Actually, Professor Gossel made a conjecture that almost all graphs are controllable. So these two authors, they proved this conjecture. So from this conjecture, from this theorem, actually, we know immediately that almost all graphs, then they have the same work numbers if only if they are generalized co-spectral. I think this theorem, I give some ideas of the proof. So first we need a theorem of Svetkovich, Dub, and Sachs in 1982. So it gave a formula for the work generating functions in this way, this formula. So from this formula, we can see if you know the generalized spectrum of the graph, then you know the generating function. That means you know the work numbers, all the work numbers of any length of the graph. So here is a very short proof. So we just prove the necessity part. To suppose NJ equals NH, because we already know NKJ equals NKH for every K, if only if NJ equals NH. We use the Cayley-Hamilton theorem, then we get this equation. So here we use the fact that G is a simple graph, then C1 is 0, equal to the trace of A minus the trace of A, so it's equal to 0. Let W1 be the submatrix consisting of the first n minus 1 columns of W. We use bar n equal to W1 transpose multiply W1. It's a submatrix consisting of the first n minus 1 rows and the first n minus 1 columns of n. So we write the subscript 1 to be Cn minus 1 up to C2. So it's a column vector of length n minus 1. Here Cn minus 1, they are the coefficients of the characteristic polynomial. So using this notation, then this formula can be written this way. We can obtain this equation. Okay, let's denote tilde n to be capital N subscript n. We use this another vector. So you can see this just some column, the nth column of the of W of n of the Hankel matrix n. So basically, this one can be obtained from n. Then we get another. We actually here we left multiply this equation by W1 transpose. Then we obtain this formula. So suppose the rank of Wj is greater than or equal to n minus 1. Then you will see this matrix. This matrix is non-singular. So we can solve C1, capital C1 uniquely. So expressed in this way. From here, you can see the characteristic polynomial is determined by Ng. So Nj equals Nh would imply they have the same characteristic polynomial. And also by this formula, once we have the same generating two graphs, they have the same generating function, the same characteristic polynomial, then they will have the same characteristic polynomial for their complements. So that's we have this one. So just a remark. Actually, after we read this paper, we found another result by the three authors in 1989. Recall G and H are co-main, and then if they have the same main eigenvalues and the same length of projections of E onto the eigenspace S lambda for all eigenvalues of lambda, main eigenvalue lambda. So they have this theorem. G and H are co-main if only if all the work numbers of G and H coincide for k from 0 up to n minus 1. If only if nkj equal to nkh for all k greater than 0. Actually, however, we found the first part does not hold. We found a counterexample for the first part. You see, here the paragraph. Their sequence of numbers like this. So the graph has 8 vertices. So for these two sequences, the first 8 entrants they are the same, coincides, but the two sequences are different, and they have distinct main eigenvalues. So probably this k should be 2n minus 2, should be 2n minus 2, not this number. So I think we may think the proof may be fixed, I think. So actually our proof is, we give another proof, shorter proof of this theorem. They prove this one using from other ways, I think. So now the problem is now reduced to given the information of the number of works, or equivalently, the Hankel matrix Ng. Now, how can we tell the graph G is determined by generalized spectrum in terms of NJ. So given the information of NJ, how we can say the graph J is determined by spectrum? That is equivalent to the graph J is determined by its number of walks. So I just give some rough ideas for how to show a graph to be determined by generalized spectrum. So graph J on n versus is called controllable or almost controllable if the rank of its work matrix is n or n minus 1. And we shall denote by script J, subscript n, and script h, subscript n, the set of all controllable graph and almost controllable graphs on n vertices. And a rational orthogonal matrix is the orthogonal matrix with a rational entrance. And the Q is called regular. If QE equals E, that means all the raw sum of E of Q is equal to 1. We shall denote by using this notation the set of all n by n regular orthogonal matrices with rational entrance. And the level of a rational orthogonal matrix we denote by LQ or L is the smallest positive integer k such that KQ is the integral matrix. So in particular, LQ equals 1 if and only if Q is a permutation matrix. So here is a basic strategy for how to show a controllable graph to be DGS. Suppose G is the controllable graph and H is the graph generalized co-spectral with G. Then H must be controllable, and there exists a unique rational orthogonal matrix with constant raw sum, such that AJ and AH are similar via Q. So they are rational orthogonal similar. Then for every G, controllable graph G, we define this set. It consists of all regular rational orthogonal matrices, such that Q transpose multiply AJ multiply AH is the adjacency matrix of some other graph. So we use this notation to denote all the rational orthogonal matrices in satisfying this condition. So for a controllable graph, then G is determined by its generalized spectrum if only if the set capital gamma G contains only permutation matrices. So the main strategy is to show for every Q in capital gamma G, its level is 1. That is a permutation matrix. So based on this strategy, we have this theorem to suppose the determinant of WG divided by this number, which is also always an integer. Suppose if this one is odd and square free, then the graph G is DGS. So based on this theorem, we are it's very easy to get the following theorem. So suppose the determinant of NG take square, the divided by this number. So this number must be an integer. So if this number is odd and square free, then G is DGS. So this term follows immediately from this equation. So from this one, we can know we can express the determinant of WG through the square root of the determinant of NG. So for controllable graphs, the question is very easy to answer. Which graph are determined by their total number of walks? So if this condition is satisfied, then the graph G is determined by this generalized spectrum and is also determined by its total number of walks. So next, I think our as for almost controllable graphs, So for almost controllable graphs, it's a little bit complicated to show whether G is DGS. So recall the WG is a work matrix. Then we modify the last column of W and we obtain a new matrix bar W. So we replace the last column by another vector, gamma G. Well, gamma G is like this, is obtained by this vector divided by an integer. So it's very easy to show this vector gamma G is always an integral vector. And psi G is a vector. Actually, is a WIN is an algebraic cofactor of the IN entrant of WG. So we replace W by this matrix, modified matrix. And in 2021, we got this properties for this matrix. So suppose G is an almost controllable graph, then gamma G have this property, has the following property. The gamma G is a non-zero integral vector. And the gamma G is in the null space of the transpose of WG. And also have this equality. In particular, if H is another graph generalized co-spectral with G, then H is also almost controllable. And psi G and psi H, they have the same length. So from the above we can really obtain for controllable graph, the rank of bar WG is equal to n. Of course, we replace this last column with another vector in its null space, actually. Also, we can obtain gamma G transpose gamma G. This is a number. It's the length. It's the square of the length. Is the integer. We can show it's always an even number. So in this paper, we have the following result. So suppose G the controllable graph and H is the graph generalized co-spectral with G. Then we have exactly two regular rational orthogonal matrices such that this equation holds. Q transpose AGQ equals AH. For a controllable graph, we have a unique Q. And then for almost controllable graph, we have exactly two such Q, regular rational orthogonal matrices. So based on a similar idea, we can define hat gamma G, similar as before. Also for almost controllable graph, there is some unique properties. Like G is a almost controllable graph, then there is a non-zero vector. Actually, it's a unique up to a sign. It's an integral vector, such that all their entrants are co-prime, such that U is in the null space of transpose of W. And also, U is an eigenvector of A. This is matrix A with the integer eigenvalue lambda 0. And moreover, the square of the length of U is even. So this is some there's very special properties of a almost controllable graph. So let gamma G, we write gamma G in this way. Then if we denote the greatest common divisors of gamma 1, gamma 2 up to gamma n by this one, suppose D is their greatest common divisor, then U is equal to, or then you can be written this way. Because, you know, the rank of W is n minus 1. So its null space is one-dimensional. So both U and this one, this guy, that two integral vectors, also their entrants are co-prime. So they must be equal, or they are different by a sign. Next, we define another matrix Q0 in this way. So this matrix is actually the householder matrix, and it's easy to verify. The Q0 is a symmetric rational orthogonal matrix, and whose level is just this one, U transpose U divided by 2. So you see, because this number is even, so it can be divided by 2. So L0, so it's an integer, it's a positive integer. So also we have this lemma. Suppose G is a almost controllable graph, and let Qlim be the householder matrix. Then we have this one. We have this equation. Moreover, we have the level of Q0 divides the determinant of bar W. So this is something different for almost controllable graphs and controllable graphs. For almost controllable graphs, we have this criterion for almost controllable graph to be DGS. Suppose G is almost controllable graph. Suppose L0 equals 1, or L0 is an odd integer. And then graph G is DGS only if this set contains that can be hat gamma G can be written as the union of script PG. It denotes the set of all permutation matrices, and here script Q0G. It contains all the matrices obtained from Q0 by permuting its columns. So based on this theorem, we can show whether a controllable graph is almost controllable graph is determined by its generalized spectrum. So finally, we need another definition. The discriminant of graph G, we denote by a capital delta G, which is defined in this way. So there is a well-known relationship of delta G, the discriminant, and the resultant. So we have this equation. From this, we can very easily to see the discriminant of G is always an integer for a graph G. So next we shall need two theorem actually by Wang and Yu in 2016. Suppose G is almost controllable and Q belong to hat gamma G with level L such that Q transpose A G Q is a 0, 1, 1 matrix. Then let P be any prime factor of L, then P divides the discriminant of G. That means any prime divisor of L must be a divisor of the discriminant of G. So here's another theorem. Suppose Q is a rational orthogonal matrix with level L such that this guy is a symmetric integer matrix. Then suppose P is the outer prime factor of delta G. Then if P squared does not divide the discriminant of G, then P is not divided of L. So based on this theorem, actually in 2022, it tells they give the following theorem. For a controllable, almost controllable graph G, we let the determinant of bar WG can be written in this way, where B the outer integer, and suppose L0 either equals 1 or it's outer prime, such that L0 precisely divides determinant of this guy, the determinant of bar WG. And the second, the greatest common divisor of B and the discriminant of G, they are co-prime. If these two conditions holds, then G is determined by generalized spectrum. So the question is now is how to interpret the above theorem in terms of NJ, because we only know the information of the work numbers of length up to 2n minus 2. So we know the information with NG. Then how can we obtain a theorem like this theorem? So it's not difficult to show the following properties can be deduced from the Hankel matrix NG, whether graph J is controllable or almost controllable. We can, from NG, we can compute the characteristic polynomial on all the eigenvalues if J for a controllable or almost controllable graph G. We can also compute the discriminant of G, and also compute the non-main eigenvalue, the only non-main eigenvalue lambda 0 G. So actually, we do some calculations. So let's compute this determinant of bar WG. Is a new matrix obtained from WG by replacing the last column by another vector, gamma G. So we expand the determinant of W bar WG by the last column, then we can obtain these equations. This is very simple, I think. Moreover, we can also have this kind of relation. Well, W1 consists of the first n minus 1 column of W, and bar WG equal to W1 transpose multiply W1. It's a submatrix consisting of the n minus 1 rows and the first n minus 1 columns of the Hankel matrix NJ. So once we know NJ, capital NJ, then we know bar NJ, capital NJ. So also we have this kind of relation. So we have the following theorem. We define tau G to be this number. So this number can be computed from NG. Then we have the following theorem. Suppose the rank NJ equal to n minus 1. Let L1 to be the greatest common divisor of tau G and the discriminant of G. And suppose L1 equals 1, or L1 is the outer prime and tau G is not a perfect square. Then we can show J is DGS, and hence is determined by its total number of walks. Here, I like to remark both the quantity, the parameters, tau G and delta G, they can be computed through the knowledge of N capital G, capital NG. So this above theorem gives a criterion for almost controllable graph to be determined by its generalized spectrum, and as a result, to be determined by its total number of walks. So the proof actually is not very difficult. It just follows, I think, follows from this theorem using new conditions in terms of NG. So I just skip the proof. Finally, I like to show you some examples. So let G be a graph of order n equal to 9. We are given the sequence of number walks like this. then we can obtain the Hankel matrix J from this information. Then we get the rank of NJ is 9, so the graph is controllable. And this number is equal to 23, which is odd and square free. So the graph G is TGS, and is determined by this sequence. Here is another example. Also, it's a graph on 9 vertices, but there's a different graph. There's a different sequence of work numbers. Then we can obtain NJ, the rank of NJ equal to 8. So it's an almost controllable graph. We can obtain tau J equal to the 23 square, and del J equal to this number. So they are co-prime, then L1 equal to 1. So the conditions of the theorem satisfied. So J is DGS, and hence is determined by its total number of works. So here's another example. Still is on 9 vertices. So is this a sequence of work numbers? Then also the graph is almost controllable. We can compute a tau G from this information and delta G. So L1 equals 3 is a odd square, not a perfect square. So the conditions of theorem satisfies, and G is DGS. So the graph is determined by the total number of works. I also give you last 2 examples. Here is a pair of controllable graph on 9 vertices. Actually, they have the same sequence of work numbers, but the condition of the theorem does not hold because this is even and has a square factor. So graph G is not determined by its total number of works. So since these 2 graphs are non-isomorphic, but they have same work sequence of work numbers. Also, this is another example. The 2 graphs, they are non-isomorphic, but they have the same sequence of work numbers. And also the condition of a theorem does not hold because this one is not a prime. So from these 2 examples, we can see that the condition of the theorem in some sense is tight, actually. If the condition does not hold, then we have some counterexamples. And also we do some enumerations. We enumerate all graphs up to 9 vertices. So we just look at the last column. So this number is the number of graphs on 9 vertices, and among which this is the number of controllable graphs, and this is the number of controllable graphs that satisfy the conditions of our theorem. That means this is the number of graphs they are determined by their work numbers. And this is the number of almost controllable graphs. And this is the number of almost controllable graphs that are determined by their work numbers. So okay, let me give a brief summarize. So we show for most graphs, the question which graphs are determined by their total number of works actually is equivalent to the problem of generalized spectral characterizations of graphs. And based on this, we give some criterions in terms of the Hankel matrix NG, provided the graph J satisfies the rank of NJ is greater than or equal to M-1. That means it's controllable or almost controllable. For these graphs, we give some simple criterion for them to be determined by the total number of works. But however, we do not know how to generalize our method to graphs with if the rank of NJ less than or equal to N-2. in particular, I think we are more interested in the case when the rank of nj is equal to n minus 2. We do not know any counterexamples, whether the work number, the sequence of work numbers can determine the generalized spectrum or not. So actually, if the rank of the nj is very small, suppose is equal to 1, so definitely I think the theorem or our result does not hold, because for any two regular graphs, they have the same velocity, say they have same number of work sequence. So if the rank of nj is very small, so I think the sequence, the work sequence contains very few information about the graph. But if it's comparatively large, I think stop here. Thanks for your attention.
Thanks very much. Are there any questions? I have one question, which is probably not very simple to answer, but what if instead of controllable, you assume that the characteristic polynomial is irreducible? Does that make any difference? Does it make some proofs easier?
Sorry?
Well, your hypothesis, you're looking at graphs with controllable graphs and asking questions about isomorphism,
Yes.
number of walks. And I'm asking, what if you replace the assumption controllable by the assumption that the characteristic polynomial is irreducible? That's slightly stronger than just.
So the signal is weak. Actually,
No, if the characteristic polynomial is irreducible, the graph is controllable. There's no problem.
so actually in this talk we work numbers. For the sequence of a closed number of works is equivalent to the spectral information, the spectral characterizations of graphs. But
Yes.
For our question, which graphs are determined by their work numbers, I think it's something different. So in most cases, it's equivalent to the question of generalized characterizations of graphs. So in this case, we can give some criterions for graphs to be determined by their work numbers. But in other cases, we cannot say anything. So if the rank of the work matrix is small, so it's less than equal to n minus 2. So I got you. Sorry, I now hear clearly.